My name is Ricardo Costa, and I'm from the University of Minho, and I'm going to present the work me and Miguel have been developing for exaFOAM. So we are mainly interested in viscoelastic fluid flows for industrial relevant case studies, processes. And one of these processes we proposed to analyze and to benchmark in the exaFOAM project is called extrusion. So since I believe most of you are not familiarized with what extrusion is, I brought here a simple video. So we have this big machine, and we have here a feeder, if you can see my mouse, and inside this feeder we put polymer pellets. Then these pellets are forced through this barrel where they are heated, and they move because of this screw is rotating. And at this end, we have a die where the material is forced to go through, and after that, it gets the shape we want. It has some post-processing processes as cooling or cutting off, whatever we need to perform. So conceptually, the process is simple. What makes it difficult is the viscoelastic nature of the material we are dealing with in this process, because these polymeric materials often exhibit a counterintuitive rheological behavior that makes the process controlling challenging, and therefore producing high quality parts as well. And I should have gone to the next slide. That's it. As you can see in these images, it was a study we performed here. Fortunately, we can rely on computer simulation tools to design these components and to control the process, but still dealing with polymeric materials brings considerable difficulties. So at the end of the day, often these simulations are performed considering simplified models, which are easier from the computational point of view, but they fail to properly represent the physics in the process. So these difficulties arise both from the numerical and computational sides, as I will show in the next slides, and I will start with the modeling aspects. So I will not go into details because I believe you are more than familiar with these kind of equations. I just want to stress that the most general momentum equation is called the Cauchy equation. And this equation involves velocity, as usual, the pressure, and also the stress tensor. So we usually have 10 variables, but if we assume that our fluid is Newtonian, as I will show in the next slide, then we can explicitly replace or substitute this stress tensor, and we end up with the Navier-Stokes equations, which only involve our variables and are therefore easier to solve. So to what comes to the fluid rheologically modeling, we can classify it in, three categories. We can assume that the fluid has no internal stress and it's an inviscid fluid, and for us it's not the case, and it's not interesting to analyze. Then we can assume the fluid is Newtonian, which means that the stress is linearly proportional to strain. And since we have this very simple relation, we can, as I was saying before, directly substitute it in the Cauchy equation, and we get the Navier-Stokes equation because we don't need to compute the stress. But some fluids also exhibit this non-Newtonian behavior. And in this case, the usual approach is to split the stress tensor into two components, one for the solvent and the other one for the polymeric part. And here where the most difficult part comes. So the most easy way of trying to modeling a non-Newtonian fluid is to consider it as a generalized Newtonian fluid. What it means? It means that I will assume that my polymeric stress is null and my solvent stress is very similar to what I have to Newtonian in the Newtonian case, but I will simply replace the dynamic viscosity by an effective viscosity. And this effective viscosity then follows some law. In this case, we have the example of the power law, which is very, very standard. But these models fail to reproduce the elastic nature of these materials. Although they are better than using a Newtonian model, they still fail to reproduce this elastic nature, which can become very important in these processes. So in that case, we have to go for these linear or non-linear viscoelastic fluids. And there are two main differences that I want to stress. The first difference is that now we have some PDE to solve, or a set of PDEs to solve, which means that our system of equations, PDEs to solve, before we had the moment equation, continuity equation, if we want the energy equation, and that's it. But now we need to add a couple more equations to this system, because now I cannot obtain this stress tensor explicitly as I could before in terms of the strain tensor. The second aspect I want to stress is that uh, while the solvent part is given as for the Newtonian case, and the polymeric part is given, is given, as I was saying, from solving a PDE, I also need often to consider or to split this polymeric component into several components that we call the modes. Why do we need it? Because when rheologically we characterize the viscoelastic material, there are two parameters that we usually measure. These parameters are the G prime, so the storage modulus, which represents the elastic portion of this viscoelastic behavior. And if you want, it describes the solid state behavior of our material. And we also have the G double prime, which is the loss modulus, which characterizes the viscous portion of the viscoelastic behavior. And it can be seen as the liquid state behavior of the material, if we want. So we get some data from the lab. We have some equations to fit. We want to fit these equations because they contain the parameters that I was showing before. So if I go to the previous slide, you can see that I still have here some eta parameter and lambda parameter. Lambda is the relaxation time. So I need to experimentally obtain these parameters and then to fit these equations to the data so I can obtain these parameters. And in this case, it's the relaxation time, as I was saying. And if I assume one single mode, you can see that the fitting is incorrect. So it's very bad. But the advantage is that I just have one stress tensor, which makes a total of 10 variables to solve in my system of PDEs. If I consider one more mode, so I have one more set of parameters to obtain and therefore also to fit, we can see that this curve fitting is much better at the cost of more variables to solve. So now I have 16 variables. I have 3 components of velocity, 1 pressure, and then I have 2 stress tensors And since they are symmetric, I have only 6 components in each, which makes a total of 16, which is huge. But it's not still ideal, so I can see that my errors in this curve fitting are still not appropriate. So I can increase to 7 modes, and in this case, that we can see that our curve fitting is almost perfect. It fits very well the experimental data, but now I have 46 variables to compute. And that's mostly what makes the modeling part of viscoelastic materials a challenge to simulate this kind of processes. So now I will turn to the numerical side. And so we have a system of equations to solve, as I was showing before. We have continuity equation, moment equation, and then we have these constitutive equations to obtain the stress tensor. And the most standard way of solving and obtaining all these variables is what we call a segregated solution algorithm. What I show here is a very simplified version of the piezo algorithm. And pretty much we start with some approximation for u, p, and tau. We solve the moment equation, we get a new approximation for velocity. Then we solve a Poisson pressure equation, we update our velocity, we obtain new approximations for velocity and pressure. And then I can obtain my stress tensor or all the stress tensors that I need. And at the end, if it has converged, okay, I can go to the next time step. Otherwise, I have to repeat all these loop again. So as you see, this involves computing each variable individually, so one at a time, and sequentially through this fixed point algorithm. The advantages are that it's relatively simple to implement. There's a relatively minimal memory footprint compared to what I will show in the next slide. And it's also relatively easy to extend to other more complex systems of PDEs or put more equations in the system. It's relatively easier. The drawbacks of this segregated approach is that there's a weak inter-equation coupling, which means that I might need to loop several times until I obtain convergence, because the solution convergence might get slow, which at the end of the day will increase my computational time. And especially if I have a complex problem with complex physics, it can be even more pronounced. Okay, on the other side, and since modern computers are equipped with much larger amounts of memory, and usually it's not a problem, especially if you can split your simulation through several nodes, we can think of solving all the equations together. So we will assemble the moment equation, the continuity equation, all the constitutive equations, and all the coupling terms between these equations that I need. I put all of it into a block matrix, into a big matrix, and I solve this. And therefore, I obtain all these variables, velocity, pressure, and stress, in all together. So at one loop, at one solution of this big block matrix. So obviously the drawback here is that I need much more memory, which usually is not a limitation. And the benefit is that I get a stronger inter-equation coupling that we expect to speed up solution convergence and therefore decrease computation time. That's what we expect from these block-coupled solution algorithms. Towards or in the perspective of exascale systems, block-coupled solution approaches also have a couple of interesting features. One of them, as I said, we reduce the number of iterations we need to perform these fixed point iterations. And because of that, I reduce the number of times my processors communicate, which is good. On the other side, I increase the workload of each processor because each one of them has a larger system of equations to solve, and therefore I have more floating point operations in relation to the number of messages I need to change between processors. On the other side, and inevitably these messages are bigger because I have more data to exchange, which can be a challenge concerning the communication balance, latency, bandwidth. And from the numerical point of view, from the linear solvers point of view, it can also be challenging because it's more difficult to preserve the M properties of this matrix, and therefore I can have some deterioration of efficiency or convergence, especially if I have a complex problem. But all these issues, that's what we want to analyze in the exaFOAM problem, in the exaFOAM project, I'm sorry. So what are our objectives within the project? First of all, and the major objective is to make simulation with viscoelastic fluid flow problems for industrial problems compatible with these realistic models. So we don't want to simplify and to use generalized Newtonian fluids because we know they do not properly represent all the physics in there. We want to make it possible to use viscoelastic models. And obviously, currently it's possible, but it's not feasible. It's not compatible with the requirements of the industry, and especially in terms of time to solution, because it takes a lot of time, and that's what we want to decrease. And more specifically, we aim to, well, on one side, to improve the existing segregated approaches in OpenFOAM, and I'm talking about ViscoelasticFluidFoam solver available in FoamX10. And on the other side, we also want to develop and test and analyze these block coupled approaches because OpenFOAM already has a base block coupling infrastructure that we can use. So it should be relatively simple to extend this for our type of problems. So we are still far from the end goal, but we have been obtaining some interesting results, and I'm going to show some of them in the next slides. So Flavio already presented the micro benchmarks in the project, and in what concerns viscoelastic problems, we have this simplified extrusion problem. So it's simplified because it allows to use coarser meshes, and therefore the execution time is smaller when we compare to the industrial case, and these allow us to perform some initial exploratory studies and to obtain useful insights and useful sensitivity to these base solvers, both the segregated and the coupled solvers. Okay, so when we put this test running, and in this case we consider a Giesecke's viscoelastic law with 6 modes. I have a 1 million cells mesh, and as I said before, we use viscoelastic FluidFoam solver. And we can see that the residual of each of these variables stagnates. We aren't able to converge to the solution. At some point, it gets stagnated and it becomes like that for the rest of the simulation. This is because stability reasons, and we know that problem already from other situations. And okay, before that, obviously, just to show that at some point, because of our current number limitation, we cannot proceed more with simulation because our time step becomes so tiny that it makes no sense. But that's one of the consequences of this instability. So, as I was saying, this is one of the problems that we know very well from previous case studies that we performed in here. And one of the techniques already implemented for the UCM, for the upper convected Maxwell model, is this improved both sides diffusion. So this technique mainly consists in adding a diffusive term on both sides of the momentum equation, and obviously on the left side it's treated explicitly. I will compute it based on the previous approximation of velocity, and on the left side I compute it implicitly, and this helps us to stabilize this solution procedure. So as I was saying, it was implemented already for UCM. We extended this to the Giesecke's viscoelastic law. And as you can see now, we can converge smoothly and reach the steady state of our problem without any major difficulty. And obviously, as I showed before, and in this case, just to confirm that our velocity, our maximum velocity in the problem converges to some value, and as a consequence, our delta t is reasonable and also gets stagnated at this value. So going to the industrial case, now you can see that we have a much more intricate profile extrusion die. So this obviously implies that we need a much larger mesh, or if you want a finer mesh, and we consider both 20 million cells or 40 million cells. Both cases are available in the repository, and the goal here is that we are going to really replicate what happens in the industry with a real case scenario. Okay, and again, if I use the base Viscoelastic Fluid Flow solver, again with the Giesecke's viscoelastic law with 6 modes, I obtain no convergence starting from some point. And obviously I cannot proceed with this simulation because time step becomes very small. Velocity magnitude at some point makes no sense to our problem. But if we implemented this improved both sides diffusion, now everything runs smoothly apart from some spikes that we can observe. And to be honest, we still don't know the reason of these spikes, but they seem to be very short in time. So it happens and very quickly everything goes back to normal. And at the end of the day, we can obtain convergence of all variables and we can reach the steady state solution. But we still need some time to dissect these spikes, which are very strange, but so far we don't have an explanation for it. So if it happened to you in some problem with this solver or with other solvers, please let me know. Okay. So although we haven't focused so far in the computational aspects because we have been trying to solve all these numerical issues. I just want to mention that I have performed these simulations in the ARM cluster from BSC, and it has been a very useful experience to gain sensitivity and also useful insights, because one of the goals of the project is also to test the performance of OpenFOAM in different architectures, including ARM. And we haven't performed some preliminary studies, but I don't want to discuss it. If you want, you can do it offline. But in this presentation, I don't want to do it because I still need to detail more what we have done. And first of all, we need all these solvers working smoothly without these problems that I have shown you. So that's the end of my presentation. If you have questions, please feel free to raise them to me or to Miguel.